Good morning. As you know that this course has already been uploaded, and from there you have seen that what are the topics we will be covering, and I have also given a little on what applications it will have. So, any process engineering, this process does not mean that it is only associated with food, but it is associated with any chemical, biochemical, any kind of processing where it is being used, and this being on fluid, that is momentum transfer through fluid. So, we have any fluid which is coming across in any processing. This course will be very helpful for them both in understanding and in application. So, you will be very much benefited if, of course, we will be giving you some assignments, some solved solutions, so and some understanding of the application of the respective topics or respective aspects. So, that you see when it is coming, as and when rather it is coming. As you know, it is a 12 weeks course, and it will be covered, rather it will be covered in 60 lecture classes, and assignments will be altogether different. They will be also uploaded in due time, and any doubt, any moment, anywhere. And in one more thing, let me tell you, in some of the cases purposefully, when I will be dealing with, in some equations there could be something wrong. That was purposefully done, so that we would like to know whether you are following it rightly or not, or just like that you are following. So, you must also see if there is any mistake and bring to my notice. Definitely I will tell whether that was right or that was wrong. Right? This is done purposefully, so that you can find out if there is any flaw. That will help you to understand more in detail if there is fault, and you can identify the fault. That is the most primary thing, that if you are able to identify. Right. So, in momentum transfer, when we are talking about, definitely fluid will start from the very basic definition of fluid, equation of continuity. That will be our beginning of the entire course. So, we will start from there. So, when we come to that momentum transfer in process engineering, then you will see we are starting with, there are two types of fluids. One is compressible fluid and the other one is incompressible fluid, right. So, we will start with compressible fluid, and the equation of continuity, from there we will start, right. And in that case, you will see that this is applicable to many unit operations in processing, like flow behavior of the fluid, that in many cases that is important, and when it is important, that time these equations or these applications, these topics will be very much useful. Now, let us define what is fluid, right. So, a fluid we define in such a way that which does not permanently resist distortion, and hence will change its shape, right. So, those substances which will not have permanent distortion when you are subjecting it to any force. So, that we call to be a fluid. For example, you have seen at home also, when you are keeping water in a water bottle, then it is taking the shape of the water bottle, whereas when you are keeping it in the pressure cooker, it is taking in the shape of pressure cooker, right. And in the pressure cooker you are applying force, but still it is there, and it is not, if you take back after giving some force, if you take back, open it, you will see that the same water was there. That means, it is not undergoing any permanent deformation, right. Local, temporary, that could happen, and that analysis has to be done. Examples, of course, as I gave, that in liquids are, water is one liquid, vapors, and they obey this kind of liquid behavior or fluid behavior, right. Carbon dioxide gas, oil, milk. Milk is another very handy example. Handy example why I say, both water and milk, which we come across every now and then, isn't it? We come across every now and then, primarily water and then milk also. And if you take it to be a application of food, then milk is one such fluid which is very widely used and processed in dairy industries. But that indicates that this is a fluid which we can definitely take care, or this can be an example of the fluid, right. Then there are, as we said in the beginning, there are two types of fluids. One is incompressible and the other in compressible fluid. Now, incompressible fluid is that which inappreciably affected by change in pressure, right. For example, most of the liquids are like that, means if we give pressure, then the changes are not appreciable. So, that we have to keep in mind. So, like say water, if we give some pressure to that, its property values are not significantly changing. So, those whose property values are not significantly changing with little pressure or adequate pressure, that is called incompressible fluid. Whereas, the other one, compressible fluids, they are, if subjected to pressure, they are changing their properties, their behavior, and in that case we call them to be compressible fluid. So, we start with that, and mostly now we will be handling with the incompressible fluid, right. Then we come to, because we are saying we will start from the equation of continuity, then what is the continuity, right. What do we understand by the term, by the word called continuity? So, a fluid is considered as a continuous distribution of matters or continuum till a smallest volume of fluid contains a large enough number of molecules, so that a statistical average is meaningful and the macroscopic properties, for example, density, pressure, etc., smoothly or continuously they change from point to point, right. So, that means this small volume, that is, as we the term called infinitesimally small, right, as small as we can think of. Infinitesimally small, this word meaning that as small as we can think of, and if even in that, this is where this volume will have sufficient number of molecules, so that a significant meaningful behavior in terms of the property values like pressure. Pressure is not of course property, but density under pressure, they are significant. They can be also having a continuous behavior. So, in that case we call it to be a continuity, right. So, then let us come to momentum transfer, right. So, we will come that momentum, this word is coming from the definition, how the definition is coming momentum, right, where from it is being derived, that will come subsequently. But momentum can be either fluid at statics or fluid at rest, or fluid dynamic under dynamic condition, that is fluid in motion, wherein momentum is transferred, and this transfer is known as momentum transfer, right. Normally, we also call it to be transport of momentum, depending on where from you are taking the sources, means book, which book you are following. Depending on that, it may have this term also, the transport of momentum, or normally generally we call it to be momentum transfer, right. So, when we look into the overall part of this momentum transfer, then we call that overall mass, energy and momentum balances are on arbitrary finite volume called a control volume. Now, this control volume can be like this, that if we take this small volume, right. So, this can be said as to be a control volume, and so if this and surrounding is all around this is the surrounding. So, if we can derive the properties or equations based on this control volume, which we can integrate into the entire environment or entire place where this fluid is associated, right. So, this control volume is that where the things needed are state of inlet and outlet of the streams and exchanges with surroundings, right. So, there will be of course, in this control volume one inlet and one outlet. So, if it is inlet and if it is outlet, so if we say in a pipe, so if like that, so if this be the pipe, right, sectional view, then this we can say to be inlet and this we can say to be outlet, right, and this will have a finite control volume, right. So, a differential element for a control volume is normally used. In this control volume, we will take the differential element, and differential balance is made in a single phase and integrated to the phase boundary using the boundary conditions. There, one thing we have to keep in mind, that as we said, that we will be doing everything based on this control volume, but if we integrate over the entire fluid domain or boundary of the fluid, knowing the boundary conditions, then we can say this in what deduction or derivation is valid for the entire fluid, right. Then we always start with the differential equations. Mind it, one more thing I should have said in the beginning, that for understanding or for pure derivation of this subject as a whole, if you have a good knowledge of the differential equations, then that will help you to understand very much, because all the time it may not be possible for whosoever is being teaching that going into detail into mathematics than into the physics. So, we will be handling more on the physics than on the mathematics, right. So, we expect that you understand the differential equations, and that will help you a lot. So, if any deficiency in differential equation handling, please try to get into that and then come into this subject. It will be very good for you and helpful to understand. Okay. So, always we will start with the differential equation of the conservation of mass and momentum in general, and unwanted terms, if there be any, will be discarded. That is the easiest part, that if there be any, you will see that subsequently when we are proceeding rather, then you will see that there will be some terms which may not be having that much significance on that particular topic or on that particular matter, that may be discarded, right. Now, differential momentum balance to be derived is based on the Newton's second law and allows to determine variation. What are the things which we can determine with the help of the Newton's law, that one is variation of velocity and position and time, right. So, velocity, if we assume it to be infinitesimally small, right, and it will have, if we said this is the inlet and if it is the outlet, right, then this, and if we assume it to be very small, rather it should have been, this is the pipe, right, rather this will have velocity in this direction, right. And when we are determining this velocity, this Newton's law will tell us that how the variation of velocity with position and time, right. Normally, anything which is independent of time, that we call to be under steady state, right. But if it is not independent of time, rather if it is dependent on time, then we call it to be unsteady, right. During that period it could be unsteady or steady depending on the situation which will come across, right. So, other things which we can also derive from the Newton's law, that pressure drop in a laminar flow, and also we can find out the turbulent flow with certain modification of that laminar flow equation. So, if we take this thing, then we can proceed further. Now, then we come to, then what is the Newton's law, that is the second law of motion. What it is saying? It is saying that the rate of change of momentum of a system is equal to the sum of the forces acting on it that acts in the direction of the force, right. As you see that it is nothing but the summation of the forces, right. This is equals to dP over dt, right. Obviously, this we can say this P to be equals to mv, that is the momentum. So, these equations are called the changes of equation or equation of changes, which tells the variation of properties with position and time. Now, we should also know certain things. These are preamble or prerequisite for the subsequent equations or subsequent derivations. So, that we should also know, like some mathematical terminologies like partial time derivative. Now, partial time derivative, which we express as del rho del t, right, this way del rho del t, this way we express to be partial time derivative. Now, where it is said that if the variable is say density, then the partial time derivative of this density can be written as del rho del t, and this indicates that a local change of density with time at a fixed coordinate of x, y, z, if we take it to be the x, y, z coordinate. Similarly, r theta z or r phi theta. So, depending on which axis you are taking, that will indicate whether we are taking x, y, z Cartesian coordinate or cylindrical coordinate, right. So, this is then partial time derivative. Then total time derivative. Total time derivative is that if velocities in x, y and z directions are say dx dt, say dx dt in the x direction, y direction dy dt, and in the z direction dz dt, if they are in x, in y and in z directions, then the total time derivative, which is of course a function of time and velocity component, is d rho dt, and that can be written as del rho del t plus del rho del x into dx dt plus del rho del y into dy dt plus del rho del z into dz dt, right. As I said that there can be some mistakes in the thing which if you can identify, then let us know and we will definitely let you know. I hope here you have seen that there is one mistake already there which can be identified. This is for your understanding, I am just telling. Otherwise, these things I could have obviously beforehand corrected and made it okay, but purposefully I am not keeping, because here you see in this particular one where we said that d rho dt is del rho del t plus del rho del x dx dt, that is the velocity component, this is the time derivative, right, and plus del rho del y dy dt plus del rho del z, it should have been del z del t, right. So, it is dy dt, instead of that it should be dz dt, right. So, this you please check and then bring to my notice as and when you come across. So, there will be obviously one communicating media through between you and me, where you can ask whether this is correct or not, and definitely I will let you know whether it is right or wrong. This kind of mistakes in cases I have particularly kept for you to identify. So, the identifying the mistakes will make you understand more in depth than just following. This you keep in mind, okay. And it could be that yes, it could have been absolutely there could have been no mistakes, but I do not want, because I want you to identify. Okay. Then another time derivative, that is called substantial time derivative, which is also defined. This substantial time derivative is known as that the derivative that follows the motion, right. So, we can say d rho dt, this is of course, you see the operand are, here it was del, here it is capital D, right, d operand. So, this operand d rho dt is equals to del rho del t plus V x, the velocity in the x component, del rho del x plus V y, velocity in the y component, that is del rho del y plus V z into del rho del z, right. So, this is called substantial time derivative. Now, this is applicable where V x, V y, V z of course, are the velocity components in the respective directions of x, y and z, right. So, velocity component of the V, if V is the velocity, then its x, y, z components are V x, V y, V z. Now, for understanding of this, I can give you one example very good, which many of the books you may get, or if you are not coming across, then rather it is very helpful. That suppose you are standing on a bridge, right, and down below on a bridge over the lake, and down below there is your one lake is flowing. Now, you know that if there is a lake, say this is the lake, right, and there is water in it, and the water, depending on the air flow, how they will be having a one unidirectional normally. If there is a turbulence, if there is very much, when there is storm and other things, that is different, right. If there is a storm, then there could be turbulence in this, but otherwise normally what we see that this is having a unidirectional flow. And say you are standing over this, there is a bridge, and you are watching there be, let there be some fish, right, let there be some fish, and you are counting the number of fish, which we can tell to be the density of the fish in the pond, right. Now, when you are static on a point here, say if you are static on a point here, say, right, you are static from on this point, and if you and of course, these fishes they will move all around, right, and that will not be dependent on the direction of the flow of this stream, they will move all around. So, if you are finding at a definite location x, y, z of this, and if you find out the density of fish at that location, then we can call it to be partial time derivative, that is del rho del t. The del rho del t, which we said, that can be said in this case, that this is del rho del t, right. And if you are again standing over there, not now you have come down, okay, you have come down, and you are moving with a speedboat, say with a speedboat you have taken, and that speedboat you are moving, and assume normally speedboat we know this direction, x, y, z direction, unless it is submarine kind of thing, it is not possible, but you assume that you can have that facility also, then you can flow, you can move in any direction, right. So, you can move in the x direction, you can move in the y direction, you can also move in the z direction. Now, if we are also moving, and then if you count the number of fishes at a location, then that will be on the second one, which we said this, the total time derivative, right. So, in that case, this total time derivative d rho dt, right, is del rho del t, right, that is the density of the fish with time, plus del rho del x, right, that is the location at x, how the density is changing with the velocity dx dt, which is likely you understand that your speedboat, if you are moving very slowly, so that will have a velocity. If you are moving in a higher speed, that will have another velocity, right. So, obviously, you are watching that how many fishes you can count. In that case, that velocity will be a factor. So, there it is coming into this term dx dt, right, and that location density del rho del x, right. Similarly, when you are going to the with the velocity rather dy dt, that is this velocity, if you are moving in the y direction, then it will be del rho del y dy dt, and similarly for the z direction del rho del t dz dt. So, this is called to be the total time derivative. Another example. Third example which we can give for the substantial time derivative, that can be said that when you are not moving, in first case you are standing on the height of that bridge. Second case, you are moving with the speedboat, by which with the velocity of the boat you have taken care of that velocity of the boat, and then you have found out total time derivative. But the third one, if you are allowed, say you are, in many cases you have seen that you are moving with the canoe. Now, canoe is, that means there is no speedboat or driven thing, you are moving along the stream, right. So, when you are moving along the stream, then if you see that what is the effect, and in that case the stream will be, or your velocity will be in the direction of the stream only. So, it may be at some time it is in the only x direction, it may be at some time it is only in the y direction. Obviously, for all practical purposes, what example we are giving here, z direction normally not normally, but you assume that any one of these x y can also be taken as to be equivalent to z, then we can say also z direction. So, if you are moving with the canoe in the x or y or the z direction, then the changes in the density of the fish counting, that is, in this case density means not the fish density, number of fishes per unit volume, that is the density of the fish we are talking about. So, if that density of the fish to be there, you can count them in on the canoe, moving along with the canoe in the direction of the stream flow. In that case, it will be that substantial time derivative, or capital D operand, capital D rho, capital D t, that is equal to del rho del t, right. That is the time derivative of the density, plus V x, that is the velocity component in the x direction V x, and times del rho del x plus V y times del rho del y plus V z times del rho del z, right. So, depending on this definition, right, we have given explicitly this because so that you can understand. Subsequently, you will see when we are proceeding towards continuity of equation, equation of motion, equation of continuity, in all these cases these derivatives will be utilized, right. So, substantial time derivative, total time derivative and partial time derivative, these three will be very much needed in subsequent development. So, what we learned today is that what is the fluid and what is meant by fluid, and how the Newton's second law of motion we can utilize, and then how the different terminologies of the mathematics, that is the derivative, what we say partial time derivative, then differential total time derivative, and then substantial time derivative. These three we have learned. So, in the next class definitely we will go into the equation of continuity. Now, when we go to the equation of continuity, as we said the definition of continuity, when we define continuity, that is a small volume as much small you can, that is will have sufficient number of molecules, so that it will have a meaningful that is the property values will be meaningful, and that it can represent the fluid. In that case, that small volume will be taken as the control volume, and we will then add on or integrate, whatever we call add on or integrate, and over the entire domain, or which we call to be the boundary. So, on the boundary and depending on the boundary conditions, these solutions will be found out, right. So, I hope in the next class we will again start with the equation of continuity. Okay.